how an algorithm can measure that correspondence. Shall we check values one by one? Right? A naive way would be to check values one by one, but there are so many possible values. If there are million rows and thousands of or hundreds of inputs, we are going to spend a lot of time on one-to-one correspondence and then ranking. There is a shorter way. It is based on information theory. Information theory gives us an interesting metric that measures how pure a data set is. For example, this target variable contains 5 values, and if we put 0 here, then this data set with all values as 0 is a pure data set. The measure of purity of a data set is referred to as entropy. In information theory, we use this measure to calculate how pure a data set is or how impure a data set is. If all values are same, impurity is 0. If half of the values are one type, half of the values are of another type, then impurity is maximum. So entropy ranges between 0 to 1. On x-axis, if we put the proportion of positive values in the data set, if 0.5, 50% of the values in the set, in this variable, are class A and 50% are class B, then our entropy will be 1. If all values are from class 0, then entropy will be 0. If all values are from class 1, then entropy will be 0. So on y-axis, if we put entropy or the impurity of data set, we refer to it as h of a variable x. On x-axis, we have the proportion of examples that are positive or negative. When half the examples are negative, half the examples are positive, impurity is maximum. Entropy is maximum. We calculate entropy by adding the probability of every value. So what is the probability of 1 in this data set? 1 by 5. Multiplied by log base 2 of 1 by 5. And then we add this with another amount minus probability of, what is the probability of zeros? 4 by 5. Multiplied by log base 2 of 4 by 5. If there are other values, we just keep adding probability of ith values divided by 5. If we have 0, 1, and we also have 2 or 3 or 4, as many we have, we keep on adding the probability of that particular value in the set, in our variable. How many times, what is the probability of observing that value? We add this all up. In short, summation of probability of ith value of x multiplied by log base 2 of the probability of ith value. We sum these up. It gives us what? Entropy, the purity or impurity of the data set. If all values are same, data is pure. So entropy will be 0. When all values are mixed up, every value has same proportion, uniformly distributed. If there are 2 values, half of them are 1s, half of them are 0s, then entropy is maximum. This is what we get from information theory. Why we want to do this? Because we don't want to check correspondence between target and input variables, one by one correspondence. And for a large data set, it will be a tedious job. We are constructing a metric that can give us the same insight that we initially built by looking at the values of x1, x2, and x3 and their correspondence with the target, and we selected x1 to be the best variable. Now we have this entropy that measures the impurity of our target variable. Why we need this? We want to find a way to reduce this impurity. So if we know the value of x1, how much this entropy of target reduces. If we calculate the entropy of target, it is 0.72 right now. You can go ahead and calculate. Minus probability of 1 is 1 over 5 multiplied by log base 2 of probability of 1 in target, plus minus probability of 0 multiplied by log base 2 of probability of 0, which is 4 by 5. Take log base 2 of 4 by 5, multiply it by 4 by 5. Don't forget to put minus there. And 1 by 5 is the probability of 1. Log base 2 of probability of 1 is, again, log base 2 of 1 by 5. Add these two numbers, you will get the entropy of this small set of 5 elements, which is 0.72. Entropy is a measure of impurity. It measures how much information we have in this variable. If all values are same, no information. If there are many different values, there is some information we can learn from it. The information content of a variable, it can be measured using entropy. The more impure the data set is, right, the more uncertain we are. If a traffic signal is always green, what's the use of that signal, right? If it is always red, what's the use of that signal? Unless signal turns on and off, no use, right? So a variable, target variable, zero entropy means we are not interested in that variable at all. Doesn't matter if it is target or input variable. We need maximum entropy variables. Only those variables will be interesting. So one way of looking at entropy is to see it as a measure of information content in the variable. So target variable, the impurity for now in this variable is 0.72. H of target, or the entropy of the target is. Now, this entropy of target is 0.72. If we know the value of x1, if we split this set of 5 based on the value of x1, can we reduce this entropy? We can. Let's use x1 to reduce the entropy. So if we use x1, whenever value of x1 is 1, how many values of target we get? 1. Whenever x1 is 0, how many values for target we get? 0, 0, 0, 0. So target variable can be split into two buckets, two pockets, two subsets. One subset has 0, all members 0. One subset has all members 1. Now we want to calculate the entropy of this subset when x1 is 1. Entropy of x1 equals 0, we want to calculate that. So when all the members have same values, entropy is 0. All the members have same value, entropy is 0. We multiply this entropy with the weight. So weight for this node is, weight for this set is 1 over 5. Plus the weight of this set is 1 over 5. This is expected entropy, averaged entropy. After splitting, before splitting, the entropy of target is 0.72. After splitting, after we know x1, and we use x1's values to split the values of target, the split data, the subsets now, their entropy multiplied by the weight of the subset is referred to as expected entropy of target. The original entropy, say 0.72, minus the expected entropy is a measure that is going to help us choose which variable should be the best variable to split target on. This measure is referred to as information gain. Information gain is entropy of the target minus expected entropy of the target given x1. So when we know information about x1, target set will be split into multiple subsets. Every subset, we will calculate its entropy, multiply it with the weight of the subset, and then add all the subsets entropies, weighted entropies. We will get a number. That is our expected entropy. Expected entropy is subtracted from the entropy of original set. This amount, the reduction in original entropy when we know the value of an input variable x1 is referred to as information gain. Information gain is the criteria that we can use to rank these variables. Which one is the best one to describe target? Which one corresponds to target better than others? How do we choose? In our decision tree, which one will be at the root of the tree, which one will come next, which one, what variable is not needed at all? We will decide how, not randomly. Remember, in a decision tree, if all variables are binary, like our example data set, and target is binary, how many possible decision trees we can make? 2 raised to power 2 raised to power number of examples. It's a huge number. This many possible trees can be created. This many possible values there can be, and therefore this many decision trees. How, in a big search space, how do we choose the best tree? We cannot do one-to-one correspondence for big, large data sets. That's waste of time. We are going to use this entropy. We first calculate the entropy of target, and then we see one by one the expected entropy of target. If we split it on x1, if we split it on x2, if we split it on x3, we subtract the entropy of target minus expected entropy of target given an input variable. This gives us information gain. So IEG for when we subtract entropy of target from expected entropy of target when x1 is given. So information gain from x1, information gain from x2, information gain from x3. We will see which one is better, best. We will keep that variable in our decision tree. That variable may not be able to split all values correctly. Some values will be incorrectly. Some of the subsets will be maybe impure. So we will use another variable to decide about those values. But using this heuristic of information gain and selecting variables one by one help us avoid this calculating one-to-one correspondence to look at the best variable. It's a greedy search way, but effective way to search important variables in the data set and putting them in right place in the decision tree. All right. So for x2, we will do what? When we split it on x2, whenever value of x2 is 1, we have the value of target is at that time 1, 0, 0. And whenever the value is 0 for x2, this time the target is 0, 0. So this set is pure. The entropy will be pure. However, this set is not pure. So entropy will be non-zero. We calculate entropy, multiply it by 3 by 5, because we have now 3 values here. And this entropy of the subset for 0 will be 0 multiplied by 2 by 5. The weight of this subset is now 2 by 5. We have 2 elements here. We add them up. This is our expected entropy. So expected entropy of x2 of target given x2 will be subtracted from the original entropy. That will be the information gain of x2 and so on for x3. Let's look at this spreadsheet now, which is automatically calculating these metrics for us.